two-dimensional plane or three-dimensional space. So to about taking. So I hope that you can hear my voice. Sorry, delayed some time to set up this. So if you can hear my voice, I will proceed. Okay. So the lecture 9 is about a partial differentiation, about taking derivatives for functions of multiple variables. So we will introduce a lot of concepts in this lecture related to partial derivatives. Okay. So since we consider function defined on a two-dimensional plane or three-dimensional space, so where x, y, or z are the variables in the function, so we would use the following notation. Okay, so if we use a bracket with x, y, it represents a point on the two-dimensional plane. If we use a triple of numbers, to denote the point in the three-dimensional space with three coordinates x, y, z. Okay. If we add an arrow, okay, then it represents a vector. Okay, a two-dimensional vector or three-dimensional vector, depending on how many components we have. So a triple of number with vector with an arrow represent a vector. Without an arrow, represent a point in the 3D space. Okay, and you recall that you have learned the derivative of a function. The derivative of a function is simply defined as the rate of change of the function. The change of function value divided by the change of variable. If you, for example, if the variable change by h, the function value change by the upper side. The ratio is the rate of change. And this rate of change, when h tends to 0, is called derivative. Okay, so derivative is the rate of change when h tends to 0. It's the instantaneous rate of change. There are many different notations for derivative. You can use the prime, f prime, which denotes the derivative of a function. Or you can also simply use this d over dx, put this operation on f, represent that you take derivative on f. So the two notations are the same, representing this derivative, limit of the rate of change. Okay. This is a function of a single variable x. If your function contains multiple variables, not only x, but also x, y, z, for example, then the definition of derivative more complicated. For function of single variable, you have learned a lot of such formulas. For example, derivative of constant is 0 because constant never change. If it never change, the rate of change is 0. Okay? And derivative of x is 1. Right? Derivative of a polynomial is a polynomial. Okay? You have learned this. And you need to remember all of these formulas. The derivative of exponential function is itself, and derivative of sine function is cosine function, and so on. You need to remember all of these formulas. Okay, these belong to function calculus for function of single variable. For function of two variables, we can define similar concepts called partial derivative. Partial derivative means that you consider one variable as a fixed constant. For example, if you take derivative in x, you actually consider y to be constant, and you fix y, but not change y. Y is not changed, and this rate of change is only for the x variable, and therefore when x variable change, the rate of change represents the partial derivative in x. And similarly, when you take a derivative in y, you consider x to be a constant, only let a variable y change. And this rate of change is called a partial derivative in y. So if you have a function of two variables, x and y, there are two partial derivatives. You can take derivative in x and you can take derivative in y. You have two partial derivatives. Okay. So when the partial derivative in x is simply the derivative of the function in x variable, when y is regarded as a fixed constant. So according to this definition, you can easily calculate the partial derivative of a given function, provided you have the expression of the function. For example, you have expression of the function f of x, y, right? And if you take derivative in x, basically you regard the y to be a constant. So this is a quadratic polynomial in x. Y is simply a constant. Okay? It's not a variable, it's constant when you take derivative in x. So for quadratic polynomial in x, you know how to find the derivative before. You have learned this because, for example, derivative of x squared is 2x. So this term becomes 2x. Okay? And derivative of x is 1, right? This x disappears after you take derivative. You get a y left, right? And for this term, this is a constant. You regard y to be constant when you take derivative in x, but derivative of constant is 0, so you don't get anything from this part. So you get a 2x plus y. This is the partial derivative in x. Okay. And if you take the partial derivative in y, you should fix x as a constant. You regard x to be a constant. This is a constant. Derivative of constant is 0. You don't have this part. So, and if you take derivative in y, and you get 1, right? Derivative of y is 1. So you get a x left from this term. You get x. And for cubic polynomial, for x to power 3, for y to power 3, you take derivative in y, you get a 3 times y squared, right? This is the rule you take a derivative for a function of single variable. You regard y to be the variable and regard x to be constant. Okay? So it's easy to compute partial derivatives, provided you know how to compute derivative for a function of single variable. Okay? And if you look at the second question, if you take partial derivative in x, you regard this y to be constant, right? It's just a constant. Cosine y is a constant. And you take the derivative in x, you simply get cosine x times cosine y plus 2xy. That's partial derivative in x. That's the result. Very simple, right? You get a cosine x times cosine y plus 2xy. That's for the second question. Well, if you take a partial derivative in y, you should consider sine x to be constant, and you take a derivative in y. You find the derivative of cosine y, which is negative sine y, right? You get negative sine y here with negative sign. And the second term is the linear function of y. When you take derivative in y, you get 1. Okay? 1 times x squared. You simply get x squared. Okay? Very simple, right? And I would leave the third question to you. You try to complete this by yourself. Okay? You try to work out the partial derivative of this in x and in y by yourself. But I give you the answer, but you should find know the details, okay? How to derive this. So we have different notation for partial derivatives. Okay? You can use prime with subscript x representing that you are taking derivative in x. If the subscript is y, then represent that you are taking partial derivative in y. Okay? And these simply represent the standard partial derivatives with the notation we just used. Of course, you can also use this symbol to represent an operation such that if you apply this operation to f, you get a partial derivative in x. Okay? If you apply this operation to f, you get a partial derivative in y. It's like an operation on f, which yields the partial derivative. Okay? And you can also define a second order partial derivative. Second order partial derivative in x is simply the partial derivative in x of partial derivative in x. Okay, and the second partial derivative of in x and y, you can consider this to be first taking partial derivative in y, and then take a partial derivative in x here. Okay, so it's still the partial derivative of partial derivative. You take two partial derivatives, but first take a partial derivative in y, then take a partial derivative in x. Of course, you can reverse the order. First take a partial derivative in x, and then take a partial derivative in y. You can reverse the order. They are equal. Okay. So the mixed second order derivative, this is called a mixed second order derivative. You can interchange the order. You can first take partial derivative in y, then take partial derivative in x, or you can reverse the order, but they are equal in general. If the function has a second order partial derivative and a smooth partial derivative, then they are equal. So you can define various different second order partial derivatives. Okay? Just take partial derivative twice. Okay? And you can also define a higher order partial derivative, like nth order partial derivative. Nth order partial derivative means that you take partial derivative in y many times, and then you take a partial derivative in x many times. In total, you take partial derivative n times. So this is called nth order partial derivative. Okay. And let's compute the second order partial derivative of this function. Okay. So you know that just now you have already computed the first order partial derivative of this function, right? So if you take a derivative in x, you get a 2x plus y. Okay? Remember, you get 2x plus y. That's first order partial derivative. What if you take another partial derivative? Okay, so you remember that you get a 2x plus y. If you take one more derivative in x, you get a 2. The coefficient of 2x is 2. Okay, 2x plus y. If you take one more derivative in x, you get a 2. If you take one more derivative in y, you get a 1. Okay? So that's how you get this first two second order partial derivative. Okay, but the third one is different. You need to take a partial derivative in y twice. Okay, so let's first take a partial derivative in y once. If you take one partial derivative in y, you get x plus 3 times y squared. So x plus 3 times y squared. If you take one more partial derivative in y, this is 3 times y squared. Its derivative would be 6 times y. Okay, so just take a partial derivative twice. So I think that you should fill in the gap between this, because I only write down the answer for you, and I explained this to you, and you should carry out the details after class by yourself, okay, to check whether you really understand how to calculate second order partial derivative. Okay, if you cannot carry out the details by yourself, then you should watch the video and see how I explain this and try to work it out. Okay. Okay. If you look at the second question, well, if you want to compute the second order partial derivative in x, you need to take a partial derivative in x twice. Well, if you take one partial derivative, you would get a cosine x cosine y for this part, right? And 2xy for the second part. So let's just look at this part. The cosine, if you take one derivative, you get a cosine x cosine y. So for cosine x cosine y, if you take one more derivative in x, so derivative of cosine x will become negative sine x. Okay? So you get a negative sine x. Right? For the second term, if you take one derivative, you get a 2xy. If you take another derivative, you get a 2y. Every time you lose x, okay, lose 1 power in x. So you get 2 times y. Okay. The mixed second order partial derivatives would be obtained by first taking partial derivative in x and then taking partial derivative in y. If you look at the first term, if you take a partial derivative in x, you get a cosine x cosine y. If you take a partial derivative in y, you get a negative sine y. Okay? So that's why you have this negative sine y. Okay? And similarly, here if you take a partial derivative in x, you get a 2xy. And then you take a partial derivative in y, you get a 2x. So you just need to take a partial derivative and then take another partial derivative to get the second order partial derivative. Okay? Okay. Again, the third question is left for yourself. I didn't write the answer here this time. You should find out the answer. Okay. So the basic definition is simple. You just take partial derivative as you did before when you take a derivative for function of single variable. Exactly the same. You just need to regard the other variable to be constant when you take derivative in this variable. So for a function of a single variable, you have a formula called a differential formula. It's called total differential. Total differential tells you how much the function value change if the variable change. For example, if the variable changed by delta x, what is the change in function value? Very simple. According to the definition of derivative, derivative should be rate of change, right? Rate of change is the change of function value divided by delta x. So when delta x tends to 0, the limit value would be the derivative. So when it's not tending to 0, you have approximate value. Okay. So the left side denotes the change of function value. Right side denotes the derivative times delta x. Okay. When delta x is infinitely small, you would get equality. So the left side denotes the change of function value equals the derivative times change of a variable x. When delta x is infinitely small, we use dx. Okay. So this is the total differential for function of single variable x. Okay. If you have a function of 2 variables, like a function f of xy, then we still want to know what's the change of function value when the variables change. For example, if the variable x and y change simultaneously, then we can rewrite this change of function value into 2 parts, decompose it into 2 parts. We just insert such a function value, subtract this, and then add this back. So actually, this doesn't change anything because we subtract this and then add it back. Okay, but this helps us to decompose this blue part into 2 parts. Okay. In the first part, y doesn't change because here y is fixed. It doesn't change. Only x change from x to x plus delta x. Only x variable change. So when y fixed, the x change, you can use a partial derivative. So the first part is roughly equal to partial derivative in x times delta x, according to the definition of partial derivative in x. Okay, the partial derivative in x is just approximately the rate of change of the function value when y doesn't change, only x change, right? This corresponds to the first part. And for the second part, x doesn't change. You see, x is not changed, only y changed. And this red part would be equal to partial derivative in y times delta y. Okay. And since delta y is very, very small, if it is infinitely small, you can omit this part. And then you get this total differential in 2 dimensions for function of 2 variables. So the left side represents change of function value. Right side represents the change of function value due to the change of x, and another part is the change of function value due to the change of y. So because change in x variable and change in y variable can both affect the value of the function, can both lead to change of function value. And therefore, change of function value, it consists of 2 parts. First part is completely due to the change of variable x. The second part is due to change of variable y. Okay. If you have only one variable x, y will not change because you don't have second variable. Then you only get the first part, and that's just this formula. That's just the total differential of a function of single variable. Okay? If you don't have variable y, you have this. This is exactly the first part. Okay? If you don't have variable y, you only have the first part, don't have the second part. Okay? So that's consistent with the formula for function of single variable. Okay? This is the formula when you consider a function of 2 variables. If you consider a function of 3 variables, x, y, z, then the change of function value would be consisting of 3 parts, including the last part, which is due to change of variable z. Okay? Because now you have 3 variables. If any of the 3 variables change, the function value would change, right? So you have the change of function value is consisting of 3 parts. Okay. So this is the total differential, okay, similar as the formula for function of single variable. It's a generalization of the concept. And this total differential is especially useful to help us to derive a chain rule for function of 2 variables. So what's chain rule? Recall that if you have a composition of function, if you have a composition of function consisting of 2 functions, f and g. So if you consider f of gx, okay, this is a composition between 2 functions. You consider the change of the function value. Then if you regard g of x to be the variable, then the change of function value will be equal to derivative of f times the change of the variable inside f. So that would be d of g. But g is also a function, therefore the change of a function value g would be equal to derivative of g times dx. Okay, and this is called the chain rule, because this formula, if you look at the left side and only the right side, omit the middle part. It tells you how much this composition function change if the variable x change. Okay, if variable x change, the composition function would change by this amount. It's the product of the 2 derivatives. The derivative of f times derivative of g. The product of the 2 derivatives is the derivative of the composition function. Okay, this gives you the formula that if you have a composition function, you take derivative, you get a product of the 2 derivatives, derivative of f times derivative of g. Okay, this is called a chain rule. And there is also a chain rule for a function of 2 variables, and we have to use the total differential to derive this. Just like here, we consider how much the function will change if the variables change. Okay. So d of a function represents how much this function change. So let's look at the chain rule for a function of two variables. So let's consider a composition between two functions. If f is a function of pq and p is a function of xy, q is also a function of xy. Okay. Then df, the change of function value f, would be consisting of two parts. The first part is due to change of p, second part due to change of q, right? This is the total differential we just have seen. Let's look at this again. If you have a function of xy, then the df would be consisting of two parts. Derivative in x times dx, derivative in y times dy, right? Now, the only thing that we change is the notation. We change x to p, change y to q. So you have a function of p and q. That's just the change of notation. Nothing, the function doesn't change, only notation change. Then we change xy to pq. Then we get this formula, total differential. If p change by this amount, this dp is change of p, dq is the change of q, then the function change by this amount. Okay. It consists of two parts. Now you can further look at what's dp. What's the change of p? Because p is actually a function of xy, right? If p is a function of xy, then the change of p would be due to change of x and change of y. So dp actually equals the two parts in the bracket here. So, and this is exactly the formula in the previous page here. We just change f to p. If you change f to p, okay, you get the derivative of p in x times dx, derivative of p in y times dy, and that's the formula. Okay. So you replace dp by this, replace dq by a similar formula. Okay, and this gives you how much f change. And we can collect the coefficient of dx because this is something times dx, and there is another term times dx here. So you have these two parts times dx, okay? And you have two parts times dy. And if you look at the first part, the coefficient of dx, this part should be the partial derivative of f in x. Okay, so if you have a composition function, if p is a function of xy, q is also a function of xy, you can take a partial derivative in x, and this partial derivative would be equal to this part. So you need to first take derivative in p, then times derivative of p, and plus the second part, you take derivative in q plus the derivative of q. Okay, this is the chain rule for function of two variables. Okay. Actually, if you don't have q, for example, if you don't have q, you only have p, then you don't have the second part. You only have the first part, and this first part would be exactly the chain rule for function of single variable, right? If you don't have q, don't have the second part, you have the standard chain rule. Okay? When you have another variable q, you simply have an additional term due to the change of q. Okay? And similarly, if you take a partial derivative in y, okay, you only replace these partial derivatives from x to y, change x to y. Okay. So this is the called the chain rule for partial differentiation. Okay, each part, if you just look at this part, this is exactly the chain rule for function of single variable. If you look at the second part, this is the same thing, but this is for another variable q. Okay, for function of two variable, you need to sum up these two parts. Okay, so let's look at this example. Let's find the partial derivative of the function by using the chain rule. First, if your function is a single variable of theta, but theta is a function of two variable, okay? F is a function of single variable. In this case, if you take a partial derivative in x, you regard y to be constant, right? If you regard y to be constant, you only have one variable x, and you only have one variable theta. And in this case, you simply have standard chain rule that the partial derivative in x is simply the derivative of f times derivative of theta. Derivative of theta in x is 1. Okay? Theta equals x plus constant. The derivative of theta in x is 1. While derivative of f is negative sine theta. Right? So you simply get negative sine theta for the first question. Okay. So remember this and work it out after class by yourself. Give you some hint here. So this is the simple exercise, provided you know how to calculate the standard derivative. Okay. So let's look at the second part. Second question. If you want to calculate partial derivative in x, according to the formula written here, you need to calculate the partial derivative in p times partial derivative of p. Okay, so partial derivative in p, if you take the derivative in the exponential function, you get a coefficient q, right? So you get a q times this exponential pq, and then times derivative of p in x, and that would be 2x. Okay, so you get 2x times q times this exponential function. Okay, but this is only one part. This is only this part. You still need to take partial derivative in q, and then take times partial derivative of q. Well, if you take a partial derivative in q, you get a p come out. Okay? And then you partial derivative of q would be negative sine x. Okay. So every term can be computed. So if you look at this formula, every term can be computed. Then you sum up these terms, you get the result. You get a partial derivative in x of f. Right? So you should be theoretically you should be able to calculate this result by yourself, because every step you only need to compute one partial derivative. You just need to use this formula. Okay. So hope that you can work it out by yourself. And the third question is similar, nothing different. So any question about this? So make sure that you understand 60% of what I say, and then the rest 40% you should figure it out, figure out the details by yourself after class. Okay. So we have learned the partial derivatives, and we have also introduced how to compute partial derivative for function of composition type. This is called composition type. You have function of PQ, but P and Q are a function of another variable, xy, right? So this is called composition function. We will introduce how to compute partial derivative for a composition function. So these concepts can be used furthermore to define directional derivative. So what's directional derivative? Initially, we introduced two partial derivative in x and partial derivative in y. That's two partial derivatives that represent derivative in two directions, in the x direction and in y direction. Okay, so partial derivative in x is simply direct derivative in the x direction. Because when x change, what's the rate of change? The partial derivative in y is simply the derivative in y direction, right? Because it tells you when y change, how much is the function change. Okay. So what if xy change simultaneously in a given direction, a, for example? And in this case, what's the rate of change of the function? And you first need to know if a point in the two-dimensional plane moves in this direction. If it's changing in this direction, it means that the point xy move in this direction in the plane. If the point move in this direction, in the direction of a in the two-dimensional plane, and the function value would change, right? Because the function value depends on the point. It's a function of the point. Okay, the function value would change, and the rate of change would be called the derivative in this direction, because the point moved in this direction. And when point moves in this direction, it's actually on the straight line passing through a given point. For example, initially we have a point called x0, y0, and then we let this point move in the direction of a, okay? And the new point would be on the straight line passing through this point in this direction. A straight line passing through a given point in a given direction can be described by a parametric equation. Okay? For example, if xy is the point on this straight line, then x minus x0 and y minus y0 would be a vector. This vector would be proportional to this direction. Okay? So if x minus x0 and y minus x0, if this vector is proportional to the vector a, then it would be equal to a constant times this direction, a. Okay, that's why we have this parametric equation. Because if you move x0 to the left side, move y0 to the left side, you have x minus x0 equal to a1 times s. And second equation would be y minus y0 equals a2 times s. See, so this tells you that the change of x, the change of the point, is proportional to the unit vector a, and this s actually measures the distance of change. How much distance is it from the original point x0, y0 to the current point xy? Okay, the distance between these 2 points is denoted by s. If s is positive, then the point moves in the direction of a. However, if s is negative, it means that the point moves in the negative direction of a. Because if you have a vector on the two-dimensional plane, it has the opposite direction, right? If the point xy move in the opposite direction, s would be negative. So for any given point x0, y0, and a given direction a, all the points on the straight line passing through this point in the direction of a can be written as these two equations, because the point on this straight line all satisfy this equation with some number s representing the distance between the 2 points. Okay. So once you have this equation describing the straight line in the given direction a passing through given point, you can look at the directional derivative. Okay. The directional derivative is the rate of change in a given direction at a given point. So this is the notation. This notation represents the derivative of f in the direction a. So if the point move with a distance s, if it is moving with a distance s, then the point would become this point, this new point. So x component becomes x0 plus a1s. Y component becomes y0 plus a2s. And this is from here. Because this is x component, this is y component, right? When the point move in the direction a with distance s, the new coordinate xy is this. You simply substitute these two coordinates here. Okay. So the new point, the new position of the point is this. Okay. So f of this minus f at the original point is the change of function value. Okay. So if the point change by distance s, then in this direction, in the direction of a, then the change of function value will be the upper side. The change of function value divided by the change of the point in distance, divided by the distance of change. When the distance change distance tend to 0, you get a derivative. You get derivative, and this represents a rate of change in the direction of a. Okay, so on the one hand, it represents the rate of change in the direction of a. On the other hand, this is actually a derivative of compensation function, because you see that f is the function of these two variables. If you call this to be x, call the second to be y. So f is the function of xy, but x, y are function of s, right? You are taking derivative in s. You are not taking derivative in xy, you are taking derivative in s. So that's a compensation function. X and y are function of s. So according to chain rule, this derivative in s is equal to the partial derivative in x times derivative of x here, plus partial derivative in y times derivative of y. Well, what's derivative of x? This is your x, right? You take derivative in s, you get the coefficient a1. Okay, that's derivative of x. So derivative of y in s would be the coefficient a2. So you get a2 here. So eventually you let s tend to 0, right? When s tend to 0, this represents rate of change. So if you set s to be 0 in this expression, you simply get x0, y0 in the bracket without s. Okay. This is the directional derivative. It's the derivative in the direction a. So any direction has two components, a1, a2, in the two-dimensional space. Okay. So you can further equivalently write this into a product between two vectors. It's the vector a times another vector. This another vector has two components. First component is partial derivative in x. Second component is partial derivative in y. So you have a unit product between two vectors. The second vector is related to the partial derivatives, and it's independent of the direction A. So the first vector is simply the direction A. So you get direction A times another vector that is independent of the direction, okay, related to partial derivative. So the second vector has a name. It's called gradient. Okay? So this vector is called gradient. It has a special name, and our formula shows that the derivative in a given direction A is simply equal to the vector A times the gradient. Okay. So that's the formula here. Okay. This formula has a geometric meaning, which says that because the unit product between two vectors can be written as the product of the length of the two vectors times cosine theta. Theta is the angle between the two vectors. Okay, if you have two vectors, there is an angle between two vectors, and the unit product is simply defined as this, simply equal to this, the product of two lengths times cosine theta. While A is representing the direction. A direction means that A is the unit vector. Okay. So here the vector A is always unit vector. Unit vector means that its length is 1. So the length of this part is always 1. So you simply get the length of this gradient vector and this vector, see, times cosine theta. Theta is the angle between A and this vector. Okay. So cosine theta is always smaller than 1, right? It represents that this directional derivative is always smaller than the length of the gradient, because cosine theta is always smaller than 1. So it equals 1. This cosine theta equals 1 only when theta equals 0. Only when the direction A coincides with the direction of the gradient. So gradient of a function is a vector that its direction is fixed. Okay, but A can be changed. If you look at the derivative of the function in different direction, the maximum value is achieved when this direction coincides with the direction of the gradient. Okay, so the directional derivative achieves maximal value when A is in the direction of the gradient vector. If A is not in the direction of this vector, then theta would not be 0. Cosine theta would be smaller than 1. You get smaller rate of change, right? So the biggest rate of change is achieved when the direction of this gradient vector. So we have the following geometric meaning. So first, gradient is in the direction that the function increases fastest, right? Because in this direction, the derivative is maximal. Derivative maximal means that the function increases fastest. Okay. Well, what's the derivative becomes maximal in this direction, and the maximal value is simply the length of this vector. So the direction of gradient is the direction in which the function increases fastest, and the length of this vector gradient is the derivative of the function in this direction. Okay. It's also the maximal derivative in all directions. Okay. While this is the gradient, if you look at the minus gradient, opposite direction, it has opposite direction. Okay. If it has opposite direction, it means the function decrease fastest. Okay? In this direction, function increase fastest. In the negative direction, the function decrease fastest. Okay? And negative of this length represents derivative of the function in this direction, in the opposite direction of the gradient. So this is the geometric meaning of a gradient. It's a vector. Its direction and the length both have geometric meaning. Okay. Let's look at this example. So this is a function of two variables. Right? Let's find the direction in which the function increase fastest at a given point. Okay, which means that if x, y change from this point in some direction, then the function should change fastest. Okay. We want to find that direction. So note that direction is direction means unit vector. Okay, we want to find a unit vector. So we only need to calculate the gradient of the function. If you the gradient consists of two components. First component, the partial derivative in x. It's 2x, right? If you take a partial derivative in x, you get a 2x. If you take a partial derivative in y, you get a 2y. So this is the gradient. It consists of two partial derivatives. And if we look at this gradient at this given point, we substitute x to be 2. So we get a 4 here. We substitute y to be 1, so we get a 2 here. So we get a vector. This vector is the gradient of f at this point, when x, y equals 2 and 1. But this is not a unit vector. We know that the function increase fastest in the direction of this vector, but this vector is not unit vector. What we want to find is a unit vector representing the direction. So you know that you know that you want to find the unit vector in this direction. You only need to divide this vector by its length. Okay, the vector divided by its length is a unit vector. So what's the length of this vector? Length of a vector is can be calculated by Pythagorean law. It's a sum of squares under the square root. Okay, so under the square root, you have sum of squares of the two components. It's 16 plus 4. So you have square root of 20. Square root of 20 would be 2 times square root of 5. So if you divide this vector by its length, you get the blue part. You get a unit vector. Okay, the blue part is the unit vector. Okay, so therefore the answer is just this blue part, in this unit vector. This is the direction in which the function increases fastest, because this vector is in the same direction of the gradient and its unit vector. Unit vector represents direction. So we have used several concepts like direction. Okay, so in this subject, whenever we say direction, it means a unit vector. Okay, we always want to find a unit vector as the direction. We need to divide this vector by its length. If we divide a vector by its length, the direction of this vector doesn't change. its length change, but direction doesn't change. Okay. This is another example related to directional derivative. The question is there a direction in which the function, in which the derivative equals to the given number? Okay. So we want to find a direction such that in that direction, the directional derivative is equal to 14. Okay. Directional derivative equals this vector A times the gradient vector. Right? That's the formula. Okay. The directional derivative in the direction A is equal to A dot this gradient vector. Okay. This is the inner product between two vectors. So let's first compute the gradient vector. The gradient of the function consists of two parts, the partial derivative in x and the partial derivative in y. So you can calculate partial derivative in x. It give you 2x minus 3y. Okay, correct. And if you take partial derivative in y, you get a minus 3x plus 8y. Correct. Okay, and this is the gradient at a given point xy. When x equals 1, y equals 2, you would get a practical number here. It would be minus 4 and 13. Okay, so this is a vector, and you can calculate its length by Pythagorean law. Its length is square root of 4 plus square of 13. That would be 185. So this square root of 185 is the length of the gradient. The length of the gradient is the biggest possible directional derivative, right? We have learned this. So the directional derivative would be always smaller than the length of the gradient. So the length of the gradient is the biggest possible directional derivative. So we see that in this question, biggest possible directional derivative is this. However, the question asks you whether the directional derivative can be equal to 14 in some direction, right? But 14 is bigger than this biggest possible directional derivative. Okay, so it's impossible, right? It's bigger than the biggest possible directional derivative, so this is impossible. Okay? There does not exist such a direction in which the directional derivative is 14, because this number is bigger than the biggest possible directional derivative. Okay, hope that you can understand what I explain here. I can give you 5 minutes. If you have any question, you can ask. Otherwise, you can closely examine this question by yourself. Okay. There is a last part of today's lecture. It's about the Taylor series. I'm not sure whether you have learned Taylor series for function of single variable. You have learned it in this lecture, but here we need to rederive, let you know how to derive this. Okay. You recall that the change of the function value can be related to the integral of the derivative. That's the famous Newton-Leibniz formula. Right? So if you simply look at the change of function value, it's equal to integral of derivative. So you can move this to the right side, move g of x0 to the right side. Let's change x to t, use t and t0. So the integral would be from t0 to t. Okay. Now let's split the second part into two terms. Okay, so we write this derivative of g into two parts. It's equal to a derivative of g at t0 plus this difference. Okay, the sum of these two parts would be derivative of g at s. But let's decompose g prime s into the two parts, because then this part can be easily integrated out. It's constant. Integral of the constant is simply constant times t minus t0. You can write this down. And the second part, if you look at second part, you can use Leibniz formula again. And Leibniz formula says that change of this function value is equal to integral of the derivative. Derivative of this derivative would be double derivative. That's why you have a double derivative of g here. Okay. Now you can further change this double derivative into two parts. The first part is just this double derivative at t0. The second part is the difference. And the difference would become a triple derivative, the integral of the triple derivative. And this is the constant, right? Integrate a constant. Integral of a constant can be explicitly written down. You have a double integral. The inner integral would be simply s minus t0. And then you integrate s again, you would get half of s squared. So you get half of t minus t0 squared. Okay. So you have double derivative times t minus t0 squared. Okay. And then you have a remainder. This remainder is small. It's roughly t minus t0 to power 3, actually, because you have triple integral. Every integral gives you t minus t0. Okay, so this part is smaller than t minus t0 to power 3 times the third order derivative. So it's a smaller term. So let's omit this cubic term. Okay, let's only consider the first three terms: constant term, linear term, quadratic term, and the higher order term that we omit. Okay, that's called Taylor series. Taylor series says that any function can be approximated by a quadratic polynomial, okay, plus higher order terms that we neglect. Okay, so any function can be approximated by quadratic polynomial. That's Taylor series up to second order. Okay, this is a function of single variable t. What if we have a function of two variable x, y? Okay, let's first write down this one-dimensional Taylor series. A function of single variable is called one-dimensional. Okay, and for function of two variable f of x, y, we construct a function g of t like this. See? So this new function of t, this is the function of t, right? This new function of t has the basic property that if t equals 0, you get f x0, y0, when this part disappears. If t is 0, you don't have this part. You have x0 and y0 in the bracket. And if t equals 1, you get x minus x0 plus x0. So it equals x. So the x0 cancels the second x0. You get x. So when t equals 1, you get x and y. So f of xy simply equals g of 1. So when t equals 1, you get f of xy. Okay. So let's substitute the t to be 1 here. If you replace t by 1, replace t0 by 0, you get a g1 equals g0 plus 1 times derivative plus half times double derivative. Okay, this is the Taylor series for function of t. And here, g of 1 is simply f of xy, right? On the left side, you get f of xy. On the right side, the first term, g of 0, is simply f of x0, y0. See, you set t to be 0, you get f of x0 and y0. Okay, the first term on the right side is the function value at a given point, x0, y0. Okay, and if you compare this blue part with the Taylor series here for function of single variable, and you see that on the left side you have a function value, on the right side you have a function value at a given variable t0. Here you get x0, y0. So these two parts is very similar to the Taylor series here. So we only need to look at the third and the fourth term to see whether they are also similar as the Taylor series here. Okay, actually, this would be the Taylor series for a function of two variables. But we still need to figure out what is the third and the fourth term. We want to express the third and fourth term also in terms of f. Okay, for example, this term should be first order partial derivative of f. Okay, just like here, here it is the first order derivative of g, and the last term, this term should be related to second order partial derivative of f, just as here it's double derivative of g. Okay, so let's compute what is the third and the fourth term. So this is our definition. G of t is defined as this function. Okay, t is inside. It's a composition function, right? If we introduce p to be this function, q to be the second part, we have f of pq, right? Now p is the function of t, q is the function of t. If you take a derivative in t, by using chain rule, you should take a partial derivative in p, then times partial derivative of p. Well, if you take derivative of p in t, you simply get this coefficient x minus x0 here. You get the coefficient. Okay, and according to chain rule, you still need to take partial derivative in q times partial derivative of q. Okay, partial derivative of q is this y minus y0. Okay, you get a first order derivative of g. This is the expression. You see that if you take one derivative, then it's equivalent to multiplying f by this operation. Okay, so the first term here, you see, is simply apply this operation to f. And the second term here is apply this operation to f. Okay, if you apply this operation to f, you get the second term. Okay. So if you take derivative in t, it's equivalent to apply the two operations to f. Now, if we take another derivative, double derivative, okay, we just need to apply this operation to the above function and apply this operation to this function. Okay. Now, you can put this partial derivative inside. This would give you second order partial derivative in t, and the square of this x minus x0. Okay, so this is the term. And you have a cross product term. It's x times y. Okay, it's this term. And if you put this partial derivative on this term, it's a mixed second order partial derivative. Okay. Here you also get a mixed second order partial derivative. So this and this are the same actually. So that's why you have 2. You have a coefficient 2 because this term is exactly this term. They are the same, so you get 2 of such terms. And you also get a third term. A third term, you consider the product of this. You have square of y minus y0, right? And you have second order partial derivative in q because here. So you have 3 terms. Okay. So let's summarize. The derivative of g is consisting of 2 terms. Each term is the partial derivative of f. The second order derivative of g consists of 3 terms. Each term is related to second order partial derivative of f. Okay. Now let's substitute this expression into here. Here we want to set t to be 0, right? Let's set t to be 0. Okay. If you set t to be 0, you don't have this part. So p would be x0, q would be y0. So you have x0, y0 here. And the partial derivative with respect to p, initially you have partial derivative with respect to p. But this is the partial derivative of the first variable here. Okay, we simply write this as partial derivative in x. That's just a change of notation. Nothing changed, only notation change. So this partial derivative in x represents the derivative in the first variable here. Okay, so p and q become x0, y0. Here you get a double derivative of g when t is 0. So recall that we have this formula. We want to find the second and third term. Now you have it. You substitute it. You substitute this g prime 0 here. You get a linear part. And the double derivative of g give you a quadratic part. Right? You get a quadratic part and the linear part. That's the Taylor series for a function of 2 variables. This is the formula we want to derive. Okay. So if you compare this with the Taylor series, a function of single variable, let's look at this. For a function of single variable, the function can be approximated by a quadratic polynomial in T, quadratic polynomial of T, consisting of constant part plus linear part plus quadratic part, right? Here is similar. For a function of two variable, you can also approximate it by quadratic polynomial in x and y. So this is the constant part. This is linear part. Linear part means that you have a polynomial of degree 1 here. Okay, a polynomial degree 1 in y. And this red part is a quadratic term. Okay, so you have quadratic power on x and y. Okay, every term is a quadratic term. Okay, so you can approximate a function by quadratic polynomial consisting of constant part, linear part, and quadratic part. So quadratic part consists of three terms. It's related to the three different types of second-order partial derivative, right? In total, you have three different types of quadratic second-order partial derivatives, all appear here. Basically, if you take a second-order derivative in x, you need to multiply this by x squared. Okay. If you take a mixed second-order partial derivative, okay, if you take one derivative in y, you need to multiply this by change of y. If you take a derivative in x, you need to multiply this by change of x. Okay. So let's look at this question related to Taylor series. It's very simple if you know the formula. Okay, if you can remember the formula. Let's find the Taylor series of a given function at 0. So what do we mean Taylor series at a point? So this is the Taylor series at this point, okay, at a given point, x0, y0. Here for this question, we want to compute Taylor series at 0, 0, which means that which means x0 equals 0. So y0 equals 0. So you don't have x0 here, y0, you don't have this. What you would have is x, y, x squared, xy, and y squared, because x0 and y0 are both 0. Okay? So that's what we mean Taylor series at this point. It means x0 equals 0, y0 equals 0. Okay. So what we need to calculate is the partial derivatives at 0, 0. So, okay, function value is easy to compute. You simply set xy to be 0, you get 1, right? And if you take one partial derivative in this expression, you would get a square of the denominator, and according to chain rule, you get a 2 here. Okay. Now then you set xy to be 0, you get a 2. Okay. If you calculate the double derivative, second order derivative, you simply need to take one more derivative in the first order derivative. So you already know the first order partial derivative. It's written here. You take one more derivative of this expression. Then the power here would become 3. Sorry, so you actually there is a mistake here. Here the power should be 3 if you take one more derivative. But according to chain rule, you need to multiply. You need to multiply this result by the coefficient of x. Okay, so initially, if you take one derivative, you would get a negative 2 times 2. You get negative 4. If you multiply this negative -4 by another -2, you get +8. Okay. Then you substitute xy to be 0, you get 8. Okay. So this is the second order partial derivative. So you can compute all the second order partial derivative in this way. Okay. And then you set xy to be 0, you get some numbers. So here xy should be 0. Okay. This xy should be 0. So you calculated all the partial derivatives up to second order. Then you can use the formula here. This is the Taylor series formula at 0, 0. Okay, so you have constant part, linear part, and a quadratic part. Now you know these numbers. All these numbers you know. For example, f00 is 1. Okay, so you have 1 here. And this first order partial derivative is 2 and -1. And that's why you have 2 times x and -1 times y. And if you look at this second order partial, it's 8 to 4. So this is 8 divided by 2. This is 8, this is 2. This is -4. -4 times 2 is -8, right? So you approximated this function by a quadratic polynomial of xy. Okay? And this is the way you compute the Taylor series. Okay? Just substitute this partial derivative into the formula. Okay. Seems a little complicated, but calculations are straightforward. Okay. To summarize, we have introduced a concept called partial derivative for function of multiple variables, and we require you to be able to compute all the partial derivatives up to second order at least. Okay. Then we introduced a concept called directional derivative and gradient, and we conclude that the maximum possible directional derivative would be achieved when the direction is in the direction of the gradient. And the maximum possible value of the directional derivative is simply the length of the gradient. That's our conclusion. Okay? The function would increase fastest in the direction of this gradient and decrease fastest in the opposite direction of the gradient. Okay. So we also introduced a chain rule for differentiation of composition functions. Okay. And in the last part, we introduced the Taylor expansion of a function, for a function of 2 variables, up to quadratic terms. So we introduced a lot in this lecture. Okay. There are many exercise questions in this lecture. And basically, it only requires you to practice how to take derivatives. Okay. Okay, so that's all for today. If you have a question, you can ask. No one ask questions? Hope that you can understand, because multi-variable calculus requires a lot of computation, a lot of practice. in fact. Okay. So if there is no question, then let's meet in. Okay. Then let's meet in tomorrow's tutorial session. Thank you. Yes. I will send email to all students. We will have tutorial session tomorrow. Okay. But it depends on you. You can choose whether or not attend. Okay. Okay, thank you. Bye-bye.